Hello everybody. Yeah, thank you all for coming today here. My colleague and myself, we're going to present you all our method called GraphXTOP, entitled Unleashes Nuclear Performance Potential. So first of all, we're gonna give you the outlines. We wanna start with the context and performance-related stakes, the methodology, some results coming from this methodology, the human overview and decision, and after that, the benefits. Yeah, but who we are. So myself, I hold a PhD in physics. I've been working in modeling turbulence for plasma fusion, and I was integrating artificial intelligence since to design innovative methodologies in different aspects of industry. And then my colleague Olivier Malhomme.
Hello to all, I'm Olivier Malhomme. I hold a PhD in science, and I've been working in the nuclear sector for many years on digitalization, extended enterprise, on various ambitious projects like EPR2 or New World, among others.
Yeah. So I will give the floor to my colleague.
So to start with the presentation, let's picture a nuclear facility as a jigsaw puzzle. Imagine that each piece of that puzzle is functionally coherent, itself made of a lot of components like pipes, sensors, pumps, you name it. All these are more or less digitally managed on all the life cycle of said components and with a lot of activities, business roles and so on. All this produces a lot of data of very diverse sources and formats, and all these massive data produced have an impact on performance. Talking of performance, and performance is going to be the fishing line of all the presentation and the master word of it. There are a lot of stakes in the nuclear industry today that are performance related. We can talk obviously of the extension of the current operating fleet, of the high operational availability, its economical impact on outage, planned and unplanned outage, standardization, security of the supply chain. I'm not going to read you everything, but as you see, there are a lot of these. So, what GraphXTOP is about? It's about finding new ways to drive performance in complex systems and especially in nuclear projects and programs. Because of these various data we talked about earlier, we have issues of fragmented data that hinder performance, of organization silos, of information silos themselves, of troublesome data lineage that impact trust on data flows. A lot of stakeholders, as you know, in the industries, the question of sourcing, the question of cognitive load, we are going to talk about that also, and the insufficient use of simulation. We all see a lot of simulation systems for new nuclear, but when we are talking of operating fleet, that's another story. So what we do with this method, we aim to identify critical entities in performance, to show cognitive load effect and how, to visualize bottlenecks in the data flows, and to provide some way of qualitatively and quantitatively assess performance. Then we are going to reveal transversal data structure. We are going to explain to you what means data transversal structure, and even test new systems before implementation. Just a quick word about data. Imagine that we are talking of data in the most general sense of the word. That means, indeed, all the data-centric production we made up today within the context of digitalization. But it could be also a plastic supermarket bag, a plane, a paper plane, or a message in the bottle, whatever. It's all way to have information flow within a complex systems. This method can be used in two different contexts of application. First of all, we are talking about operational performance diagnostics. The idea is to have new means to scrutinize performance. The other way is to be able to test complex system prior implementation and to see whether they work as intended, they have indeed these critical entities, bottlenecks, and so on, before we commit into implementing it. And now I'm giving the floor to my friend who's going to explain how the pipeline of the method works.
So we just seen that this data can come from operational field data. It could come also from simulation data. So how does it work? The thing is, from these two sources of data, we have the operational data, either acquisition or coming from simulation. We want to use somehow this framework called TOP, for technology, organization, and people. Then the step further is the graph conversion. After that, some algorithms coming from this graph theory. And after, we have some modeling of the cognitive load, such a really relevant human factor in our methodology. And after all, critical node and data structure identification to try to tackle these bottlenecks. And at the very end, the human overview and decision. Let's talk about it a little bit more further. So this TOP framework is such a thing that it's allowing us to really try to model all the dimensions in this information system, either technology, or organization, or people, into an element called source and not an element called destination, and we're going to have this arrow for the data coming from one to the other. What is the important? The importance of integrating human systems to really to the core of this performance analysis is relevant to this industry. All the stakeholders are often taken into account, but separately, this framework allows to really try to combine, to try to really integrate all these dimensions. And the one really, and last but not least, really important thing is related to the extent of this methodology, in not including not only one process, not including not only an organization, but trying to include all of the flows in this system information. And then once we have this model coming from the TOP framework, so the next step is going to be based on the graph theory. So the graph theory very well know different methods, different algorithms have been developed across years. And what's the idea behind it? The idea is to take this source and destination I just described before and to put into nodes. Nodes, simply nodes from node 1 to node 2, and we have some data flowing from one to another. And in this direction, that is really important for us to really track the flow of information, we have it result in an oriented graph. So an oriented graph implies different well-known algorithms in the graph theory framework. And it's really important because this very well-known TOP graph are powerful in such a way that we integrate all these dimensions and it remains quite simple. It can absorb large amount of data and the large set of algorithms that have been developed are very diverse, such as hierarchical clustering or simply many algorithms. So once we have this graph conversion, so some of these algorithms coming from this graph theory that we have used for this analysis is the betweenness centrality in order to tackle the charge, in order to tackle the loads in every single node, and also the community detection algorithm. So this betweenness centrality, as I was saying, that tends to reveal the critical nodes, the potential risks, the potential bottlenecks inside the system, the information system. And the community detection algorithms is explained in such a way that it could really reveal the data interconnected substructures. So these substructures can be independent to a business process, can be independent to a process related to a parameter in the information system. It could really be transversal to all that is already well known in the information system. So once we have this implementation of the algorithms, the dimension related to the human system is based on our modeling of the cognitive load. This cognitive load is going to be for us very important because we're going to try to represent and to integrate how this human factor could be also integrated into this modeling of the whole system information. So in such a way that we are considering the task complexity, the time to pressure in a linear way, and it is resulting in a score. So once we have the score related for a node and the centrality coming from previous analysis, it could become a criticality indicator, a criticality parameter. So as I was saying, this cognitive load can impact performance and safety. The cognitive loads actually are very integrated in so many industries, such as aerospace or automotive industries. And this very human system integration is in the transition from Industry 4.0 to Industry 5.0. So in summary, we have the first step, the TOP framework modeling. Secondly, the graph conversion. In third step, the algorithm-enabled analytics, the cognitive flow integration. And once we have all these separate results, we can also combine it all in a way that we have results from the community detection. We have results from this criticality integrating the cognitive load modeling. And it could reveal actually critical bridge nodes. What is these critical bridge nodes? Actually, these bridge nodes is supposed to represent nodes that connect weak substructures that in a way we have used in community detection a weak structure A and a weak structure B. And that might be a critical bridge node at the middle of them that could really be a highly potential bottleneck and is representing a risk not only in performance but also in safety. So the goal of this methodology is to try to identify all forms of critical entities, potential bottlenecks, subsets, silos, identify key roles and the load level, and of course examine all the steps on the value chain. And yes, I will give the floor now to my colleague to explain some results based on this methodology.
Thank you. So now, thanks to my colleague, you have a good view on how the GraphXTOP works and what it can do. Now let's see some results. So first of all, what we see here is a figure for which we identified for you in 4 colors, dark red, light red, green, and blue. What means betweenness centrality? It means, in fact, entities to which a lot of data flows converge and from which a lot of data flows emerge to different other entities. So the higher the bar, the higher the number of data flows converging and emerging from this entity, making it especially critical and a possible risk of bottleneck. Here into this slide, we identified 4 of them, as I said. In dark red, light red, and green, you have technological assets. And in blue, a people entity, meaning a business role. Here we have control system, sensor system, and data management system as far as technological assets are concerned. And you've got a quality control specialist is here, especially loaded, appearing in blue in the slide. Second, we talk about this thing of community detection. What it means that regardless of organization, regardless of business processes, we have some part of our perimeters that are especially linked together as far as data flows are concerned. And that shows here, and we identify in our data set here 4 clusters, named for the sake of the presentation: data centralization, operation control, decision-making hub, and safety and efficiency. And again, I want to stress again that point. They are not connected to organization. They are not connected to business processes. That's what we call transversal data structure. Then we cross this community detection with the analysis on how these subclusters are connected together. And in these examples here, you see that we represented cluster 3, cluster 2, and cluster 4. And you see that my cluster 3 and cluster 4 are linked by one single entity. My quality control specialist we already saw in the previous slide. That means that if for any reason that single entity fails, both cluster 3 and cluster 4 become isolated silos. Same applies between cluster 3 and cluster 4. When you see that we have also a single entity, this time a technological asset that links them, and if that fails, again, cluster 4 and cluster 2 becomes isolated silos. Then we talk about cognitive load. What you see is on the figure, quite simply, is how we model business centrality without cognitive load integration in red, and with cognitive load integration in blue. And as you can see, the identification of potential bottlenecks and risk for entities change drastically for people node, business role if you want. And you see that in one, our quality control specialist that we have discussed a lot in previous slide is even more overloaded here. But you also see here in the number 2 for emergency response coordinator and number 3 for engineering design interface that some people entities that appeared not very loaded, once we integrate this cognitive load, change drastically in their bottleneck risk, and that's an important thing to stress. So the key takeaway and differentiators of the method are the fact that we are able to integrate human systems with all their dimensions and especially their impact on performance, that we are able to embrace a large amount of data and especially heterogeneous data, that we are able to include all stakeholders in our modelization, in their impact on performance, and we can provide, as you saw, analysis that go far beyond the usual business processes analysis that we use usually, and reveal these cross-functional elements that are mainly hidden in other methods. And to the end, I stress again that this method can be used as well as for operational diagnostic and for simulation. Once we have all these results, what can we do with it? Obviously, we can reinforce or modify strategic teams how they are revealed in this method. We can adapt data strategy. We can refine business roles and missions. We can adapt element of organization. We can reinforce strategic technological assets, and obviously decide upon simulation. And to end our presentation, the idea is to support all the enablers of performance that are resilience of systems, digitalization, the way we articulate human, organization, and technology together, how we put humans back into the performance, and improve global digital continuity. Thank you very much for your time.
Thank you very much.
Don't hesitate to visit us at the Assystem booth. Thank you very much.